Hello, this video is to get us a sample problem on Charles's law. So let me write Charles's law right here. And we're going to do a sample problem that we have over here. First off, Charles' law, a reminder, if you went over the gas law overview video already, Charles's law is that the temperature and volume are directly proportional to each other. What that means is temperature goes up, so does volume. And conversely, if temperature goes down, so does volume, right? So as opposed to Boyle's law, where pressure and volume are inversely proportional, as one goes up, the other goes down, that's the only law that has inverse proportionality here. Everything else, like Charles' law here, is directly proportional. So volume and temperature are directly proportional. And so what we want to do is come up with an equation to be able to solve problems with that. And so as I mentioned earlier, I found that temperature and volume, we put volume on the y-axis, temperature on the x-axis, you're going to get a straight line. As you change temperature, volume is going to change to give us a straight line. Okay, and you're going to come up with some crazy equation that really doesn't make a lot of sense unless you change the temperature scale, because it turns out that all all gases, all samples of gases, gave different lines with different slopes and different y-intercepts. So every gas would have a different equation, especially if you have a different y-intercept and a different slope. But if you go ahead and take and remake the temperature scale, you'll notice that uh, all the lines here met at the same place, about 273 degrees below zero on the Celsius scale. That is the origin of the idea of um, absolute zero, some temperature that you cannot go below. And so what they did is they made up a new temperature scale. Hey, this is the coldest we can make it. Whenever we go ahead and get our temperature down to this temperature, our volume goes all the way down to zero. They actually never got it down to zero. You can't actually get a volume of a gas down to zero. But if you plotted the points, they would all meet at the same point. So theoretically, if you can get the volume to be zero, it would all it would go down to this temperature. So what they did is they took all the temperatures, added 273 to them, uh, and they turned them into the Kelvin scale. And the Kelvin scale, zero is at negative 272.97, but it's actually a little. They've actually calculated a little bit higher than that. But so when you do that, now all the lines meet at the origin, and you can get a y-intercept of zero. So, just like I showed on my Boyle's law, I'll show you on Charles' law how they got this equation. This one was a little easier. You've got volume on the y-axis, temperature on the x-axis, and if you saw my Boyle's law, you probably remember that I said you probably thought you'd never see y equals mx plus b outside of an algebra class, right? It's everywhere. You just need to be able to look for it and work with the numbers. So volumes on the y, temperatures on the x, temperature in Kelvin. It's got to be specific. So what you can do is you take your y equals mx plus b and substitute it. Substitute v for volume in the y for the y, and T for temperature in the X. And as I mentioned in the last video, scientists don't like to use M for slope because M is already used for mass. So we use K as a constant. So V equals to KT plus y-intercept being zero. You get V equals to K times T. That's the equation you get. That will give you the slope of the line here. So whatever your temperature is, multiplied by K, that's going to give you your volume. And if you change the temperature, you plug in a new temperature, you get the right volume. Now what we're going to do is we're going to do this. We're going to divide both sides by T so that we're going to get V over T is equal to K. So there's a ratio. V over T. What K is, it's a ratio of V over T. And what that means is that for every change of temperature, you're going to get the same change of volume. So if you had volume at one point in time and the temperature at one point in time, that would give you this K ratio. If you change the temperature and that changed the volume, or vice versa, you change the volume and that changed the temperature, they would have to be at the same ratio. So this K is this ratio or this proportion between volume and temperature at any point in time. Change the temperature, the volume has to change, so the proportion is the same. And since V1 over T1 is equal to K, and V2 over T2 is also equal to K, they're equal to each other. So we come up with this form of Charles' law, which um, which is actually a usable one. V1 divided by T1 is equal to V2 divided by T2. Okay. If you know three of these four variables, you can solve for the fourth. Big thing on here, you'll notice that we were able to do this only because we changed the temperature to Kelvin. So whenever you use this equation, you got to change it to Kelvin. So let's do a sample problem. I've got two sample problems for that reason, for the temperature reason. So the first problem says a gas is heated at constant pressure from 20 degrees Celsius to 80 degrees Celsius. Remember, these are all constant pressure because only volume and temperature are changing. If the gas initially takes up a volume of 5 liters, what is the final volume of the gas? So you had gas at 20 degrees Celsius, it was 5 liters. You warmed it up to 80 degrees Celsius. According to Charles' law, you would know that warming the gas is going to make it expand. Okay. Think of a balloon. If you heat up the balloon without actually heating up, melting the actual rubber part of the balloon, but if you just heat it up, it's going to actually expand, is what this is saying. But to how much? That's what we use the equation for. So let's go ahead and do this problem. Okay. So let's see, where is my, there it is. So our equation is V1 divided by T1 equals to V2 divided by T2. And we have a V1 of, what did it say it was? Well, let me put here, V1, T1, V2, T2. So I can put those in here. All right, let's see. So start off at 20 degrees Celsius, went to 80 degrees Celsius. Let's go back and put that in here. I don't like about going over back and forth here. 20 degrees Celsius to 80 degrees Celsius. And the volume started at 5 liters. What is the final volume? So we started at 5 liters, 5.0 liters, and we're looking for the final volume. So we're looking for V2. We're looking for this one right here. Okay, now remember I said that you needed to use the Kelvin temperature. And remember, to get from Celsius to Kelvin, all you do is add 273. So 20 degrees Celsius is going to be 293 Kelvin. 80 degrees Celsius is going to be 353 Kelvin. Right? 273 plus 80 is 353. Okay, and that ratio of 353 over 293 is different than the ratio of 80 over 20. So it's going to give you the correct answer. 80 over 20 is 4. It would balloon this volume to 20 liters. We're going to see that we're not going to get that. So V1 is 5.0 liters over T1 is 293 Kelvin, right? So there's your V1, there's your T1 equals to V2, which is what we're looking for, divided by T2, which is 353 Kelvin. Okay, oops. All right, sorry. Sometimes it'll do that, and I'll have to go back and erase that. I hit the button, which I guess keeps it all. All right, it keeps drawing. All right, so we're looking for V2. So once again, in order to get V2 by itself, you have to get rid of anything else that's on the side with it. And since we're dividing by 353K, we want to do it in order to get rid of it is multiply by 353K. So we're going to multiply by 353K so that they cancel here, leaves V2 by itself. And if we did that to the right side, we have to do that to the left side. So multiply by 353K
We'll multiply that to 5.0 liters over 293K. Let me go ahead and move this here real quick so we can do this problem a little better. Okay, I guess that works. Now, since 353K cancel on the right side, we get V2 by itself on the right. On the left, 353 times 5 divided by 293. Notice the fact that we're taking 353 in the numerator and dividing by 293 in the denominator. That's going to give us a ratio of 1.2. So what that's going to tell us is that our answer for this is going to be 1.2 times bigger than the original. 353 times 5 divided by 293 is 6.02. Okay. Yeah, and that's the answer. Notice that the kelvins cancel, and that leaves us with liters, which is the appropriate volume. This could have been milliliters, could have been gallons, but in this case it was liters. Okay, and so this is how you would use Charles' law. All right, so if you have volumes and temperatures changing, you plug them in and solve for the one you're looking for. Pressure should be constant on this one. Okay. All right, so that's problem number one. Remember, if we had used 20 and 80 here, our answer would have been 20. I'm sorry. Yeah, 20 and 80 here, our answer would have been 20 liters and would have been wrong. So you can't use Celsius. You can use Celsius, which will give you the wrong answer. All right, let's do the second problem here. I'm going to use some space over here. So the second problem, there's a reason why I did the second problem. I just remembered. Actually, I didn't just remember it. The reason I did the second problem is because sometimes people have a problems solving for when your unknown is in the denominator. All right, so I'm going to do a sample problem here to remind you what to do when your unknown is in the denominator. This problem says a gas is heated to 350 Kelvin, and its volume grows from 27.3 liters to 33.5 liters. What was the original temperature of the gas? So we're actually looking for, in this case, T1. The original means the first, and temperature. So we're looking for T1. So let's go ahead and do this. So I need to go to, oops, problem over here. So I'm going to write here, just a reminder that, oops, let me draw here. Our equation is V1 over T1 equals to V2 over T2. And V1, T1, I'm just going to write these down here so we can, V2, T2. So we can go ahead and do these. Okay. All right, so what were we given? We were given 350K. That's what it was heated to, so that's a T2. 350K. They're T2. And our, what else we have is 27.3 to 33.5 liters. 27.3 to 33.5 liters. 27.3 liters to 33.5 liters. So I started this volume, got this volume when we heated it to 350. What was it originally at? That's what we're looking for. All right, so we plug in V1 is 27.3 liters over T1, which you're looking for, equals to V2, which is 33.5 liters, divided by T2, which is 350 Kelvin. Notice this is already in Kelvin. I don't have to turn it into Kelvin. It's not Celsius. I don't have to add 273. It's already given to me in Kelvin. And the reason I did that is because I want to go ahead and get to this. Now, what most people's problem is on doing this, this here, this type of problem is that they want to get T1 by itself, and so they want to get rid of the 27.3. They'll divide by 27.3, and they go, oh, okay, that's my answer, which seems pretty easy, and that would be it, except that that's not your answer. That would actually be the inverse of your answer, because you would leave T1 in the denominator. So remember, when your answer is in the denominator, or your variable is in the denominator, you have to get the variable out of the denominator into the numerator, then solve for it. So a couple ways you can do this. Number one is by multiplying by t1 to both sides. Then once you multiply by t1 to both sides, it cancels out on the left, ends up on the right, and then you have to get rid of the 350k by multiplying both sides by 350k, and then also divide by 33.5 liters to get rid of it from that side. That works, and that would be a valid way of doing it. But I think an easier way of doing this is to cross multiply. And I don't know what it is, but students love to cross multiply. And so here's a chance to do it. Right? Remember, when you cross multiply, you multiply these two numbers here, the denominator on the left and the numerator on the right, and you make it equal to the numerator on the left and the denominator on the right. So you multiply those two things, and then you solve. So let's go ahead and do that. So we're going to go ahead and I'm going to take these two things. I take these two guys, multiply them together, and I'm going to write it as 33.5 liters times T1 is going to be equal to, and I'm going to multiply these two guys together. 27.3 liters times 350K. If you want to go ahead and multiply them together and get liters times Kelvin, that would be fine. I'm not going to do it. No. So now I have an equation with no denominators in there, at least not at this point in time. Okay. So now I need T1 by itself. It's being multiplied to 33.5. So I just need to divide by 33.5. Right. If it's being multiplied to T1 by 33.5, I divide by it. Right? So they cancel. But because I did it on the left, I have to do it on the right also, 33.5 liters. And so now I get T1 on the left by itself is equal to, let me get my calculator out, 27.3 times 350 divided by 33.5, and I get 285. 285.2, but I'll just round up to 285. 285, and that should be Kelvin, right? Because liters here cancel with liters here. Leaves me with just Kelvin temperature, and that's what it is. T1 is going to be 285 Kelvin. Okay. If you want to turn that into Celsius, you take 285, subtract 273, right? To get from Kelvin to Celsius, you subtract 273, and that's going to give you 12 degrees Celsius. Okay, so 12 degrees Celsius. Although this question didn't ask, I just thought I'd throw that in there. So that's how you go ahead and do the problem. So whenever your unknown is in the denominator, like it is over here, when your unknown is in the denominator, as it is right here, you cross multiply to get everything out of the denominator, then you solve for it. Okay? Hope that was helpful. I also have another video on using Gay-Lussac's law, on Boyle's law. So hopefully these are helpful to you.